So everyone ready for the afternoon session? So we're very pleased to have Mario Garcia Fernandez from ICEMAT telling us about vertex algebras from the Hull Strominger system.
Okay, so thank you very much. Thank you to the organizers for the opportunity to speak in this exciting conference. This is what I'm going to talk about is joint work with Albeit Consul and our joint PhD student, Garcia Fernandez, who just finished his PhD. I'm particularly excited about talking about this topic here because part of the developments that I'm going to talk about on the second part of my talk have been actually developing at IMPA by Raimundo Geloni and collaborators. Okay, so let me start giving some overview about mirror symmetry and non-Kähler geometry. So the way mirror symmetry started was in physics. Physicists observed that you have two Calabi-Yau manifolds. Sometimes their associated superconformal field theories are related, are isomorphic in a suitable sense. And then this was originally just a physical observation, but actually there was a breakthrough by Candelas, De La Osa, Green, and Parks, who were able to relate this to enumerative geometry, and then this captured the attention of mathematicians, and this has been a very hot topic over the last 30, maybe 40 years. So of course, I should mention Witten, the homological version by Koncevic, and also the Strominger-Jasas approach. So I guess the person who clarified what mirror symmetry means for mathematicians was Witten in this influential paper. And he told us that if you start with this physical object called the superconformal field theory associated to a Calabi-Yau, then there are two simplifications of the theory called the A model and the B model. The A model has to do with the symplectic geometry of the Calabi-Yau, and then the B model has to do with the complex geometry. Okay? And the basic principle is that if you have two mirror pairs, whatever this means, then you're going to see that the complex geometry in one of the Calabi-Yau is going to be exchanged with the symplectic geometry on the other one, and vice versa. Okay? In particular, the complex structure moduli space is going to be exchanged with the Kähler moduli. Okay. So soon after mirror symmetry was discovered, it was observed by physicists that there are manifolds. This was Spinball, Green, and Morrison that have multiple mirrors related by flops. What does this mean? There are Calabi-Yaus, which have a very large complex structure moduli space. And in order for a mirror to match the complex structure moduli space, what you need to do is to consider several Calabi-Yaus, which are related via suitable birational transformations, and then glue their Kähler moduli on the boundary. And this was a very exciting development at the time. And the nice observation by Friedman in this paper in 1991 is that actually, when you do this process of flops, you may end up in something which is non-Kähler. Okay? And this is very cumbersome because, as I told you, mirror symmetry is supposed to exchange complex geometry with symplectic geometry, but if there are no Kähler structures, what does this mean? Okay? So the main difficulties in extending mirror symmetry to non-Kähler manifolds, and this is what I'm interested in, are, on the one hand, the lack of holomorphic objects on a non-Kähler manifold. There are very few complex manifolds, very few coherent shifts, etc. So how to define the B model in that setup? And on the other hand, also the lack of symplectic geometry. Okay? So if we want to do something like homological mirror symmetry a la Koncevic, then there seems to be no room for defining the A and B models in these manifolds.
So
and
examples that arise by flops, you still have a lot of submanifolds and so forth, but you're going to...
That's true. I'm going to tell you some more. Yeah, that's true. Yes, these are Moises. Yeah. And over the years, there has been various attempts in order to make sense of this mirror symmetry for non-Kähler manifolds. And at least from the math point of view, what we do is to get inspired by the geometry of flux compactifications in string theory. When you have a flux compactification in string theory, what happens is that your internal manifold, which is your Calabi-Yau, possibly non-Kähler, sorry, is going to have a three-form, the three-form field strength. Sorry, this is not. Okay. There is a threefold, which is going to be related to skew torsion for a suitable connection, metric connection on the manifold, which behaves like a magnetic monopole. So D of the three form is going to be some magnetic source. And this causes the fact this causes that the integral over three double straight cycles on the manifold may be non-zero. Okay? If we were Kähler, this will be 0, and there will be no flux, which is this magnetic charge. So how does this relate, the existence of this three-form flux relate to our experience on non-Kähler manifolds? Well, actually, if you start doing one of these flow processes and you end up in some singular manifold by blowing down some curves, then in some cases you can actually do a smoothing and end up in a manifold which is non-Kähler, but it has less second cohomology. And actually, Friedman proved that if you keep doing this many times, this conifold transition many times, then you end up in manifolds which are like direct sums, connected sums of copies of S3 cross S3. And these manifolds have no second cohomology whatsoever and have a huge complex structure moduli space. And these manifolds in particular have a huge third cohomology group, which is potentially related, at least morally, to this three-form flux in string theory. Okay? So what we're going to do in order to try to develop a notion of, or a version of mirror symmetry for non-Kähler manifolds is to exploit the geometry of three forms. Okay, so what are the known attempts to produce this non-Kähler mirror symmetry? One is related to generalized Kähler geometry. So motivated by the supersymmetry sigma mod by Gates, Hull, and Rocek, Gualtieri and Cavalcanti, inspired by the general geometry theory by Hitchin, have initiated a program to extend the homological mirror symmetry program to generalized Kähler manifolds. So a generalized Kähler manifolds in the most classical point of view is just given by a manifold with a metric, two integrable complex structures, which are compatible with the metric G, and then a closed three form which matches dc of omega with respect to the minus complex structure and minus dc omega with respect to the other complex structure. So then the idea, in order to develop this non-Kähler mirror symmetry in this setup, or the homological version, is to encode this Hermitian data in terms of a pair of commuting generalized complex structures on the tangent plus the cotangent bundle, on the extended tangent bundle. These are commuting and square two minus identity, and then to associate suitable categories of branes. And the problems that they have encountered in doing so is, even for the cases where the generalized complex structures are very close to being symplectic, are not too far from being symplectic, they need to incorporate quaisotropic submanifolds, etc., and no one knows how to deal with that. Okay, so this is a very hard problem. For the thing I like more, which is like the relation to metrics, actually this doesn't work very well because there is a no-go theorem. So there is this well-known result. This is kind of folklore, but actually I think the last proof of this, the definitive proof is in a paper in 2022 by Apostolov, Fu, Stries, and Yusinowski. So what this tells you that if you have a generalized Kähler structure which is Calabi-Yau in the metric sense, then this needs to be Kähler. Okay, so what this says is that if you start with a compact generalized Kähler manifold, this needs to be compact, defined by a pair of closed pure spinors in the tangent plus the cotangent bundle. Then assume that there exists this notion of Calabi-Yau, which means that the norm given by the Mukai pairing of one of the spinors is a constant times the norm of the other one. Then the corresponding Hermitian structures are Kähler and Ricci flat. Okay, let me not go into details of this because I'm not going to use it, but the analog of metric with holonomy containing SUN is too restrictive, at least for our purposes, which is to extend this picture to non-Kähler geometry. There is this other set of equations which are very interesting. which were introduced by Zheng and Yao, inspired by developments in the physics literature, Grania, Minasian, Petrinian, Tomasiello. And what they deal with, this is a geometry on a 6-dimensional compact manifold, maybe not compact, why not? You consider an SU3 structure, and then you have a pair of systems of equations which are supposed to be related by mirror symmetry. So one is the type 2B equations, which is, there is a function such that the rescaling of the 3,0 form by this function is declosed. The same if you rescale omega squared. So this is going to be conformally balanced, if you want. So the Lie form is going to be exact. And then DDC of omega is going to be some current, which we don't know what it is. And remember our picture coming from flux compactifications in string theory. Then H is minus DC of omega, and this is like the magnetic current in our physical theory. And then there is a dual picture corresponding to the type 2A equations, which relates to symplectic geometry. So this in particular implies that you have a symplectic structure on the manifold. This implies that you have a complex balanced structure on the manifold. This works nicely because these solutions are naturally exchanged under T-duality, at least in the semi-flat case. Recently, Vanini and Beduli have proved that they have dual Hodge diamonds in a suitable sense, so they behave pretty nicely. But the main difficulty in addressing this problem is that typically the presence of these sources either leads you to consider non-compact solutions or distributional solutions on manifolds. So let me mention one simple example, which is part of ongoing work with Lorenzo Foscolo, and it should be compared with the so-called heterotic string solitons by Callan, Harvey, and Strominger. So you start with a domain in C2, you take the flat metric on C2, and you take a positive function. Then you define an SU3 structure on the product of B cross C by the following formula. So you rescale the holomorphic volume form, the canonical one, and then you take this word product, which is e to the phi, the metric on C2, plus the flat metric on the C. Then one can check that if the function e to the phi is harmonic, then this is actually a solution of the type 2B equations on B cross C. Okay, a very simple solution, which is very much inspired by this paper by Callan, Harvey, and Strominger. So let's take a closer look in one particular example. So suppose you fix k points in C2, and you take n1 and k positive integers, and then you consider the following positive harmonic function. Of course, what this is a solution of the fundamental equation for the Laplacian in R4, and therefore, if we see these equations in this particular setup, not in B given by C2 minus the points, but on the whole cross C, but on the whole C3, what you see is that you give a solution of the type 2B equations with sources. And the source is localized in these planes, vertical planes, located at the points. Okay? Okay. So there are further approaches to this non-Kähler mirror symmetry. There is very interesting work by Abigail Ward and Denise Auroux about the homological approach. And what Abigail did in her thesis is to be able to match part of the derived category of coherent shifts, I mean, the Picard of a Hopf surface with a suitable Ginzburg-Landau model on a symplectic manifold. And interestingly, the fact that the complex manifold is non-Kähler is reflected on the fact that the superpotential is not holomorphic with respect to any complex structure. There is also more Hodge theoretical works by Popovicki, and also a nice paper by Aldi and Helwani that is closely related to what I'm going to tell you here. Okay, so what are the equations of my interest in this talk? As I told you, on the one hand, general scalar structures, even though they are extremely nice, we don't have the right notion of Calabi geometric on compact manifolds. On the other hand, these type 2b equations, type 2a, the right way of considering is probably on non-compact manifolds, and so there is a lot of complications that I cannot do in analogy with the well-known case of algebraic algebras. So the price I'm going to pay instead is, instead of having this, instead of considering this type 2b equations here, I'm going to take this as a model, but I'm going to smear the brain. I'm going to take the brain and smear it to a smooth 4 form, and this smooth 4 form is going to be related to a bundle. And this is going to be the geometry I'm going to consider. So how does this work? So what is a coupled instanton? So this comes from my work jointly with Raúl González Molina, who is here doing his thesis. And you can ask him all the details about this to him. So you have a n-dimensional complex manifold endowed with a principal bundle. The bundle is going to have a pairing on the Lie algebra. I didn't write this down, but I should. So we're going to have a invariant pairing in the Lie algebra of the group. And then I'm going to say that a Hermitian metric, a Hermitian form on this manifold, and a principal connection on the bundle solves the coupled SUN equation, instanton equation, if the following equations are satisfied. So firstly, the connection needs to be Hermite-Young-Mills with 0 degree. And secondly, the Hermitian form needs to have vanishing Bismuth-Ricci. I'm going to explain what it is in a moment. Finally, and this is related to the equation, to the complicated equation in this type 2b system, DDC of omega, so d of the torsion, is going to be a well-defined smooth 4 form related to the first Pontryagin class of the band. Okay? So what is this Bismuth-Ricci equals to 0, and how is it related to the type 2 system? What happens is that in the type 2 system can be written if omega is a holomorphic volume form on the manifold, which you can construct from the type 2b system just by rescaling psi. And then the type 2b system can be written, the second equation in the type 2b system can be written equally well as d of norm of omega squared equals to 0. This is conformally balanced, but actually this is secretly a condition on holonomy. This condition here implies that the holonomy of the Bismuth connection of the Hermitian structure is contained in SU3.
Minus strip projection, you may wish to write ridiculously larger.
Sorry?
You may wish to write much larger.
Why?
So people can read in the back.
Oh, sorry. Okay.
Right, ridiculously large letters.
Okay, so can you read this? This is omega squared rescale.
I doubt that they can in the back.
Okay. Let me do it huge. The Bismuth connection, the Bismuth connection is the Levi-Civita connection of the Hermitian structure minus g minus 1 half of dc of omega. And this rho b is curvature is I times curvature of nabla b on the canonical bundle. Good enough? Okay. So these equations are super interesting for several reasons. One is that, of course, you like it. One is that they are related to these Hull Strominger equations that we all love and heard about. And actually, physicists prove that they are equivalent in alpha prime expansion to the Hull Strominger system, whatever this means. Another reason why we like these equations is because they actually provide coupled instantons, and that's the name. So if you consider the bundle tangent plus adjoint of the principal bundle, you can, out of the data, you can construct a connection, D, on this bundle. It's going to be actually a metric connection with respect to G plus the natural pairing on the Lie algebra. And this connection is nabla minus curvature dA, and let me write it like this. Okay, so nabla minus is a metric connection which has opposite torsion than bismuth. So this is nabla G plus 1/2 G minus 1 dC of omega. And actually, this coupled instanton equation, what tells you is that Fd wedge omega to Dn minus 1 is actually 0. Okay? So if you want a good reason for why you should study the heterotic system or Hull Strominger system, the heterotic G2 system, is because it provides instantons in a higher rank bundle. Okay? And that is very nice. And I should advertise this ongoing joint work with Agnaldo da Silva, Jason Lotay, and Enrique Serb, which is going to appear very shortly, where we study the G2 case. Okay, so we have these nice equations which have this beautiful interpretation as coupled instantons. Note that I call these coupled instantons because little omega, the Hermitian form, enters in here, but also enters in the definition of the connection D through the torsion. Okay? So this is a very coupled system of equations. It's not just the ordinary Hermite-Yang-Mills equations. Okay, as I mentioned, any solution of these coupled instanton equations actually give you a solution of the Hull Strominger system in the ordinary sense, with the caveat that you really need to consider the connection on the tangent band to be Hermite-Yang-Mills. If you are not an expert, forget about this slide, but just wanted to mention this. And actually, there is a very nice interpretation of the equations. If you have a solution of these coupled instanton equations, actually, you have a solution of this Riemannian system of equations for the metric associated to the Hermitian form, the Lie form, and the torsion. And these are the equations which are satisfied. Let me not go into the details, but this is like a generalization of the Einstein equations coupled with Yang-Mills, where you have torsion. And actually, these equations, when you have that the Lie form is exact, they are the equations of motion in heterotic supergravity. Okay, so this is a very nice interpretation in terms of physics. And on the other hand, they are also steady generalized Ricci solitons for a suitable version of generalized Ricci flow that we are currently studying in work with González Molina here and Jeff Streets. Okay.
Do you know, does it imply that D is integrable as well, or just sort of?
Yeah, it does. Yes. Yeah, I didn't write it, but it does. Yeah, let me not write it. Okay, so far so good. Are there any non-Kähler examples? Actually, yes, there are plenty of non-Kähler examples. So we are in a good shape in order to geometrize our non-Kähler Calabi-Yauxs and try to do mirror symmetry. So actually, there are, on the one hand, it is good because we can find non-Kähler examples on algebraic Calabi-Yau manifolds, where we know a lot about. So this was done in a joint paper with Andreas in 2012, and recently improved by resolved by Collins, Picard, and Yao, where they're able to prescribe suitable cohomological quantities. And then there is many solutions constructed over the years by several people on locally homogeneous manifolds. And I should also mention that there are solutions with these ansatz on T2 bundles over Kähler K3 surfaces. Okay. As I mentioned, all these solutions are really solutions of the Hull Strominger system in complex 3 dimensions, but actually, in particular, they are solutions of the coupled instanton equations as I have presented them here. Okay, this system of equations. Good. Any questions so far? So if not, let me continue. And let me tell you what does this have to do with mirror symmetry and also with vertex algebras. Okay, so the idea is the following. So in a non-Kähler Calabi-Yau, we have very little complex subobjects, maybe very little shifts. Also, we have no symplectic geometry. So if we want to study mirror symmetry, we need to specify what type of quantities are exchanged under mirror symmetry. Okay? And a nice observation in 2000 by Borisov and Likover is that the elliptic genus is exchanged under mirror symmetry under a suitable sign change. So what is the elliptic genus? The elliptic genus is the two-variable elliptic genus. This is a covariant invariant, which is defined taking a suitable integral of the dot class of the Calabi-Yau against the Chern character of a formal bundle. This is really a bundle which is a graded bundle. The bundle is infinite dimensional, but the graded pieces are finite dimensional. And this labeling here keeps track of the degree of each piece. Okay? So you do this crazy expansion, and then you obtain a two-variable formal power series, which actually, it was proved in this paper by Likover and Borisov, that if you actually take it as a function, this converges in a suitable sense and inherits natural modular properties. So it's a very nice quantity. Okay, so what does this has to do with mirror? Well, of course, what they prove is that under mirror symmetry, these elliptic genuses get preserved up to sign. So the story in relation to vertex algebras comes from the proof. Actually, the way they prove this interesting theorem is via expressing the elliptic genus as a suitable character. And what they observed is that associated to a Calabi-Yau by previous work by Malikov, Sesman, and Weintraub, there is actually a vertex algebra, which I call Vx. And this is in particular, it has more structure, but it has an infinite dimensional vector space. And it has two mutually diagonalizable endomorphisms, and you cook up this character. So this has to be understood as a formal power series expansion, where on the coefficient on element on the series is the dimension of the corresponding eigenspace for J naught or L naught. Okay. This proof actually requires a previous work by Borisov, where he studied the behavior of this vertex algebra and this pair L naught and J naught via mirror symmetry. Okay, so what are vertex algebras? Let me give you a hint on what they are, and let me try to use them for understanding a bit more what this picture is. So a vertex algebra is a structure introduced by Berger, which is very much inspired by conformal field theories. And the most basic piece of the structure is given by a vector space and a state field correspondence, which sends elements in the vector space, states, to vectors to fields, which are endomorphism values bilateral series into undeterminate set and set minus 1. This, of course, needs to satisfy a bunch of axioms. There should be a vacuum, which is a non-zero vector, locality, translation invariance, etc. The idea or the way we think of these vertex algebras is as operators on a vector space, which are labeled by points on a surface, on a Riemann surface, okay, which is this z coordinate. And actually, these axioms, locality, translation, invariance, etc., tells you how these two operators interact when they are localized in 2 points, and these 2 points go close and collide. Okay, and this gives you a suitable expansion, which is encoding an infinite number of products in this vector space. So another way of thinking of this is just a vector space, typically infinite dimensional, with an infinite number of products indexed by z, satisfying some crazy axioms, in particular this Borcher's identity. Okay, so my capital A's now turn into little a's and b's. Sorry about that, but the point is that to any element in the vector space, I can associate a set worth of endomorphisms, and then they satisfy this crazy relation. And the way of thinking about this is that I have to think of the product as taking product into different variables and then taking a suitable residue. Okay, and this virtuous identity is just a manifestation on the different ways I have to collide and take residues, and etc. Yeah. Okay, so let me give you some examples. So the first example, maybe to take in mind, it comes from the Virasoro vertex algebra. So what you think is to consider vector fields on a circle, and then these are generated by ln's minus t to the n minus 1 partial t, where t is some variable in the circle, if you want, or c star, as you like. Then this is a Lie algebra, and these are the relations of the Lie algebra. This is the width algebra. The Virasoro algebra is an infinite dimensional Lie algebra, which is a central extension of the width algebra by some element in the center. And this algebra is hooked up via this commutation relation. So C is a central element, and now the ln anti-commute via this complicated formula. Okay, so far we have an infinite dimensional Lie algebra, but what is the associated vertex algebra? So there is a way of canonically associating a vertex algebra to this, which is to take the span of this subalgebra, spanned by the ln's with n smaller than -1, plus the central element, take the universal enveloping algebra of that, and quotient by a suitable relation, which is just setting C to some constant. And actually, this is a nice model for this infinite dimensional Lie algebra, and has all these crazy relations that I mentioned before. Let me give you another example. We need two more examples, which is no-West bars. So the no-West bar algebra is given by generators ln and gn. The ln as are before, Virasoro, and then the gm's are indexed by half integers, and then you have these extra commutation relations. And this is very much related to like vector fields on a super circle, like super geometry. And now, similarly as before, you define the n=1 vertex algebra, taking a suitable Lie subalgebra, the universal enveloping algebra, and quotient by a relation which sets the central element to a constant. So the final algebra that I need is the n=2. And here we stop. Okay? So the n=2 superconformal vectors algebra is now is constructed out of a complex superalgebra whose generators are a central element, the Virasoro fields, another jn's, which are also even, and also the odd generators gm, which now come in two families, gm plus and gm minus. I didn't say it before, sorry, but already in the no-West bars, the g's in the formulas are thought of as odd. Okay, so this is a vector superspace. And these are the relations that they satisfy. And again, you cook up the n=2 vertex algebra by taking a suitable Lie subalgebra and quotient by taking the universal enveloping algebra quotient by a relation. Okay, the reason why this is a vertex algebra is not for free. There is a big theorem by Katz and Helwani, I believe, or maybe De Sole, which tells you that there is a universal construction that you can do this. Okay. Okay. So one nice feature of the n=2 vertex algebra, very much related to mirror symmetry, is the fact that it has an involution, which is given by sending L and J to L minus J, and then G plus minus to G minus plus. Okay, and you can directly see this from the relations I have written down here. So finally, now going back to the geometric picture, going back to geometry, so motivated by the story about Hamiltonian quantization on sigma models, Malikov, Sesselman, and Weintraub proved that if you have a complex manifold, then you have an associated vertex algebra. And then Borisov, using this fact, actually give a nice definition which tells you that two manifolds are going to be mirror in this vertex algebra sense if these vertex algebras canonically associated to the complex manifold have embeddings of the n equals to 2, and these embeddings are related via the mirror involution for a suitable isomorphism from this to this. Okay, so this is a very algebraic, seems to be a formal definition, but actually Borisov managed to show that for Batyrev's construction of mirror symmetry for hypersurfaces on toric varieties, this actually holds. Okay. The notation for this is not casual. Actually, the fact that these vertex algebras are constructed is taking suitable cohomology of a sheaf. So this already I said. This fits, at least in the toric setup, with the ordinary picture for mirror symmetry. And then Malikov-Sesman-Weintraub proved actually that you can do much more than constructing these vertex algebras. You can actually construct a sheaf of these vertex algebras over the manifold, and then you can take homology, and then the homology is actually a vertex algebra. Okay, to give you a hint on what this sheaf is, how much time do I have? It's like 10 minutes or?
17 minutes.
Oh, 17 minutes. Okay.
Plus questions.
Okay, good, perfect. Okay, so let me give you a hint on what this sheaf is, okay? Because otherwise it will be just words. For this, I'm going to use a nice construction by Helwani and Bressler, who proved independently that any current algebroid has associated such a sheaf. And instead of telling you what a current algebroid is, what you should think of, Enrique, tell me if this is big enough. You should think of my current algebroid as the tangent plus the cotangent of a manifold endowed with this pairing, this neutral pairing, these are vector fields 1 forms, and endowed also with a canonical map to the tangent bundle, which is called the anchor map, and also with a bracket, which is extremely important for our picture. The bracket is given by x plus g y plus eta equals the Lie bracket of x and y plus the Lie derivative with respect to x of eta minus I x I y, sorry, dg. And actually, this can be twisted, if you like, by contracting with a suitable 3-form, the torsion, which is closed, or in general, it may have further terms. In this setup, it's actually closed. Okay? In our setup, it's going to be more general. It's going to be related to this Pontryagin term. Okay, so with this specific example, let me try to explain you what this construction is. So the theorem is that to any current algebroid over a smooth manifold, you can associate a sheaf of vertex algebras. And the way they do this is in a two-step process. So firstly, they define a notion, Helwani and Katz define a notion of SUSY Lie conformal algebra, which is this bunch of axioms. So let me give you a hint of the actions, and then let me explain you the idea, which is the most important thing. So you have, on the one hand, a module for some suitable endomorphism T, a bracket which is polynomial valued. This vector space may be super vector space. Then you have an odd derivation for lambda, which squares to the endomorphism T. This is the supersymmetry. And then it satisfies some actions which, remember, like Leibniz, skew symmetry, etc. I didn't tell you, but this is actually important. This satisfies the Jacobi identity. Okay, you can stare at the actions, but let me give you the idea. The idea is the following. Really the important thing to think about, and after you have this idea in mind, you can actually derive the actions by yourself. The idea is that associated to my manifold, I consider the loop space of the cotangent bundle of the manifold. This is formally, this is infinity. These are maps from a circle into the cotangent bundle. And because the cotangent bundle is a symplectic manifold, this is formally a symplectic manifold if I fix a volume on S1. And then what this construction is telling you is that you are considering the Poisson bracket on smooth functions in here. Where sections of the tangent plus the cotangent of M are thought of as functions on M. Functions on the loop space. And you can very easily think of how these elements work, right? If I take a vector field, for example, I can contract along a map from S1 into cotangent. I will get a function and I integrate along the volume. Okay? So this is the way you cook up. And this complicated bracket is nothing more than a manifestation of this natural Poisson structure, with the caveat that the way these functions are constructed are taking integration along a loop, and therefore they have some distributional nature coming from functions on S1. And this is why these corrections to the Poisson bracket appear. Okay, so I mentioned, once you have this structure, then Helwani and Cox prove that associated to such a structure, there is a canonical universal enveloping vertex algebra. Okay, there is a canonical construction of a vertex algebra out of that. So how does the proof actually work? You start with a current algebroid, and then you consider this conformal algebra. It's given by functions on the manifold, plus sections of the current algebroid, plus sections of the current algebroid, change parity, tensor CT. You have another derivation defined by this, taking differential, etc. And then you have this particular choice of lambda bracket. So if you stick to this idea and cook up what is the Poisson bracket on the space of loops of the cotangent, thinking of these functions as distributions, you will end up with these formulas. And actually, this is an idea of Alexeyev and Strabo. And I encourage you to go to their paper.
T here is?
T is an endomorphism. It's a variable which stands for endomorphism. Nothing more than that. But it's actually, T is like derivation with respect to the little set which appear in the definition of vertex algebras in my slides. Okay, then after this construction, one takes the universal enveloping vertex algebra by the theorem by Helwani and Cox, and then you actually get the associated sheaf. And actually, what happens is that when I have an algebraic manifold, you can do this also in the algebraic category. When I have an algebraic manifold and I take E to be the tangent plus the cotangent bundle, then what you get is this chiral Doran complex of Malikos, Sesman, and Weintraub. Okay, so motivated by the previous picture, and by the previous picture is long ago. So the previous picture means this construction of characters associated to Calabi-Yau's, elliptic genus, etc. There has been a lot of work in understanding embeddings of the n equals 2 vertex algebra on the chiral Doran, and there is substantial work on the literature, mainly thanks to Helwani, Sapsin, and their collaborators. And also, of course, starting with the seminal work by Malikov, Sesman, and Weintraub on Calabi-Yau's. So our aim, and I'm going to tell you about this in the last 2 minutes. How much? Or I'm already done?
Even more? 9
Okay.
minutes.
Oh, wow. Okay, so the aim in the last 7 minutes, let's make it 7. In the last 7 minutes is to find these n equals 2 embeddings into heterotic analogs of this chiral Doran complex. Okay, and I'm going to do that using these coupled instanton equations that I told you about. So the idea is that if we have managed to find these n equals 2 embeddings for these heterotic analogs from solutions of these coupled instanton equations, then we should be able, at least morally, hopefully one day, to construct characters on non-Kähler Calabi-Yau manifolds which are exchanged under microsymmetry. Okay, and our results shall be compared with the embeddings constructed and studied by De La Osa, Galdeano, and Fisset in the physics literature. Actually, they work with general G structures And actually, I don't know if it's in your thesis material that you tackle the G2 case, or maybe Fisset, I don't know. Okay. Okay. Okay, so this section is very brief. It's just telling you what is the theorem. So the theorem is that if you have a Calabi-Yau manifold of complex dimension n endowed with a smooth principal bundle, and you assume that you have a solution of the coupled instanton equations, these equations here, then we can construct a canonical sheaf of vertex algebras associated to the solution and an embedding of the n equals to vertex algebra into the global sections of this sheaf. Okay? And the paper was posted on the archive in May 2023, and then we reposted another version last week or the week after, week before. And in the previous version of this theorem, we had a technical assumption which didn't match the physics. It was like an additional assumption having to do with a torsion bivector. And over the last year, we managed to prove that this assumption is empty. So we actually can do it in general. And we match the physical expectations. And actually, if the Calabi-Yau manifold has complex dimension n, then the central charge of this vertex algebra is 3n as expected by physicists. As a corollary, even though it's probably for most of the audience it's relevant, we can construct these embeddings from solutions of the Hull Strominger system in Calabi-Yau threefolds with, if you take the connection and the tangent bundle to be Hermite-Yang-Mills. But if you are not an expert, forget about this.
What's the 9 about?
It's 3 times 3. The central charge is 3 times the dimension of the manifold. Is the level at which you localize the central element when you do the universal construction of the n equals 2. Okay, so how do you prove the theorem? You start with your Calabi-Yau dimension n, your pairing, and a principal bundle has vanishing first point eigenclass, and you consider the coupled instanton equations given by Hermite-Yang-Mills equations with 0 degree Bismuth-Ricci form equals to 0, and this Bianchi identity on 4 forms. Omega is a positive 1-1 form, A is a principal connection. What do? You forget about all the equations but this Bianchi identity, and you use this to construct a current algebroid, similar to this picture here, but with a much more complicated bracket, pairing, etc. So associated to a solution of the Bianchi identity, you can construct a current algebroid which takes the form T plus adjoint plus T star. This is the anchor map. This is the pairing, and this is the bracket. And you see the bracket uses like curvature of A, torsion, etc. Okay, it's a very crazy gadget. Then you apply. First, I need to recast what does a coupled instanton means in terms of the current algebroid. What does it mean for the geometry of the current algebroid? The meaning of this is that you have a symmetry of the current algebra. You have a symmetry for the bracket. So you complexify this. The data of the solution gives you a pair of isotropic invertive subbundles. And then you can cook up a natural element, distinguished element, a section of the current algebroid, given by this equation that we call the D-term equation. So you choose any frames of L and L bar, cook up this bracket, and this gives you a distinguished element which is in the kernel of the anchor map. And it's this complex 1 form. And actually, having a solution of this coupled instanton equation tells you that epsilon is a symmetry. Using this, you can actually prove the theorem. So what you do now is, out of the current algebroid, I consider the associated vertex algebra sheaf. I take these specific local generators for the sheaf. I define this odd element given by this bar epsilon symmetry, and then you define this the generators to be these explicit expressions. So the J, the current is given by this formula, where U is given by this 1 form, etc. Okay, and you just cook up the relations of the n equals to 2 and show that this is an n equals to 2, and actually that this glues from patch to patch. So here I'm using a local patch in order to.
What's the convention for normal ordering? which are creation and annihilation operators?
It's hard to see from this picture, right? I can tell you in an example. Here is not so easy to see. Okay, how much time do I have? I'm done, right?
3 minutes.
Okay, do you want to see the example? Let me show you this.
It's a 3:30 on that time.
Okay, let me show you one toy example. Something very simple, no bundles, nothing, okay? No, just back to the type 2B system if you want. So you fix a complex domain in C2. Then you define a pair given by a holomorphic volume form. This is just this set 1, this set 2. And this omega, which is conformal rescaling of the flat metric on C2. And assume that this is a positive harmonic function on C2. Then, sorry, on X, on the domain. Okay? And this metric, you can see that it solves the couple instance equation with no bundle. It's just Bismuth-Ricci form equals to 0, DDC omega equals to 0. Then omega determines an exact Courant algebroid of this form here. H is minus the torsion. Is the torsion, is minus dc of omega. Then what you get from this general theorem is that you have an embedding of the n equals to 2 vertex algebra with central charge equals to 6, into the Kähler complex on this open domain in C2. And you have explicit formulas for the generators using these particular frames, which are very, very explicit. And to give you one even more concrete example, you can do as before. You can take a bunch of points in C2, take X to be C2 minus these points, then consider the fundamental solution for the Laplace equation on C2 with respect to the flat metric, given explicitly by this function. Then restricting to C2 minus the points, you get a positive harmonic function for every choice of constant. And then you have the first generator of supersymmetry, which is the most important one because from this you recover the rest of generators, is given by this explicit formula where the dots are the normal Lie product. And just to finish, let me mention that this actually seems to pretty much match a construction of heterotic string solitons by Callan, Harvey, Strominger with central charge C equals to 6 in a paper in 1991. Okay, so I finish here. Thank you for your attention.
Okay, have we got questions for Mario? Yes, Bobby.
Something like this should work for G2 superconformal algebras.
The expectation is that yes, and in the special, just for G2 holonomy metrics, there is work by Helwani, Sabsin, and Ekstrand and collaborators on this thing. Actually, they managed to construct embeddings of the Satasvili-Baffa vertex algebra into the Carroll-Perral complex, just in the smooth setup. And yeah, the expectation is that using this is probably very hard, but using the G2 version of these coupled instantons in this paper with Agnaldo da Silva, Jason Lotay, and Sarp, actually one can do a similar construction in the 7-dimensional case with torsion. So yeah, thanks.
Might be worth mentioning that Helwani and I, a long time ago, tried to do this for the twisted connected sum, but it doesn't quite work.
Actually, Mateo has worked on this with Fisset, so
superb. Yeah, I want to hear about it. Any more questions? Yes.
Can you comment on the geometric and topological implications of having mirror symmetry in this picture?
Yeah, look at this formula by Borisov, Likoper, right? So one of the things that I'm going the other way. So one of the things that you get from this formula is that at least in even complex dimensions, two mirror manifolds are cobordant. Or yeah, it's not the right true. What I mean is that they can. I mean, how is that? Yeah, they need to have the same cobordism invariant. Okay, so they may not be cobordant, but yeah, they may not be cobordant, but at least you get an agreement of this invariance. So I guess something similar can be cooked up from this picture. The point that the bundle is in place is hard to see how this is going to affect the topology of the manifold, so it's going to be a bit crazy. The dream result is that actually refining this construction and even finding more structure than the n equals to 2 embedding, you can actually cook up invariance of the manifold of the sort of like Gromov-Witten or something like that. And this can be actually done on an elliptic curve with no bundle. You can extract Hurwitz numbers from n equals to 2 vertex algebra representations on the free fermion. So the hope is, in the long run, to be able to do something like this, to cook up some sort of heterotic Gromov-Witten invariance and see if they can be, I don't know, exchanged under mirror symmetry. So that's the expectation. I don't know.
Any more questions? Well, if not, let's thank Mario again. Thank you.